Hello, so in this video we're going to kind of carry on trying to find a solution to the diffusion equation. Okay, we've looked at part one, so we've done that, we've basically shown that this thing is in fact a solution to that thing. A lot of differentiation going on, a lot of kind of new techniques, so it's well worth a watch. I mean, I know it's quite long, but it's well worth a watch just for new differentiation techniques, if nothing else. But yeah, we've effectively done that. We've shown that this thing, when we differentiate it with respect to t, and when we find the second derivative of this thing with respect to x, that, you know, and we plug it into this thing, the left-hand side does in fact equal to the right-hand side. So therefore this thing, this p of xt, must in fact be a solution to my diffusion equation. Remember what my diffusion equation was? It's just that thing, but let me just write it out a little bit neat. So it's a derivative of p with respect to t equals some d, which is what's known as the diffusion, okay, times the second derivative of p with respect to x squared. So that's the thing which we're trying to show. Okay, so now what we're going to do in this video is we're going to show that it satisfies the initial condition. So we've shown that that is a solution. Okay, but in order for it to be exact, it must satisfy some initial conditions. And the initial conditions we had to kind of make up because we didn't actually know where we started. Okay, usually we have the initial conditions that at t equals 0, we have such and such a position. We're at such and such a position. Okay, we just kind of, when we were introducing it, we just said, well, x was 0, okay? But it may not be. So we had to introduce this new thing called the Dirac delta function. This Dirac delta function, okay? And this Dirac delta function is defined by that. And effectively, if you just remember, that is just an infinitely high peak, okay, around the start point, so around x. So basically it's a width of 0. The width is 0, okay, so it's just an infinitely high peak. You know, the height is infinity, so it's an infinitely high peak. So therefore the area underneath that, which corresponds to a PDF, you know, if you remember a PDF, you know, the area underneath a PDF is just a probability density function. So it's a function which is defined by probability, okay, or which defines the probability of a situation. The area underneath it should add up to 1, so it should add up to certainty. It defines the probability. Okay, so this is kind of the whole idea behind Dirac delta function. Well, in order to do that, you know, the thing is we kind of made this function up. It's not actually a function. Dirac delta is not actually a function. So it's kind of, we need to interpret what this means. So it doesn't actually have a meaning as such. This Dirac delta function doesn't actually have a meaning because we kind of made it up. So therefore we need to interpret what this means. So basically, what does this mean? It doesn't mean that p of x is actually equal to that. So our probability function is not an infinitely high peak. Probability function is not actually an infinitely high peak. In fact, what we're saying is that p of xt approaches something that looks like an infinitely high peak. So it never actually gets to that point, but approaches something which looks like an infinitely high peak. So it approaches this Dirac delta function basically as we move from the right. Okay, so as we move from the right, so as we move towards 0 from the, so basically, what this is saying. So as t approaches 0, obviously from the positive direction, because t can't be negative in this case. We're not considering negative time. So basically what we're saying is that as t goes to 0, so as t becomes small, and so as t, what is t equals 0? That's the point where we start at. So t equals 0 is the point where we start. If I plot this out as a timeline, okay? So say, for example, if we're at this point here, as t approaches 0, what we're basically saying is we're rewinding the clock backwards in time towards the point which we started with, because that's what we're trying to show, okay? We're trying to show the point which we started with. And basically, as we go backwards in time, then the probability that the probability as we go back in time approaches this Dirac delta function. So as we go back in time, this probability, approaches this certainty. So in other words, as we kind of move away from, if I draw out now my step, my position. So say, for example, if I start at this point here, let's call this my start position, x, okay? And let's then suppose that I can move, as I move forward through time, I kind of move away from it at some point. Well, as I move away from it, I have a probability associated with, well, let's suppose I'm at this point here or this point here. Okay, but as I move backwards in time, I move back towards the point which I started with, and I can only have started in one position. So therefore, my probability is approaching 1. My probability is approaching 1 because obviously it's certain that I started at a particular point in time. It's certain that I start here. So as I move backwards in time, okay, my probability becomes certain because my probability becomes more certain because there's less places that I can be. If you like, I don't know, I was trying to come up with an analogy. If you like, I go off for a walk, right? Well, as time goes on, then basically I'm getting further and further away from home. So the places where I can be in more places. So therefore the probability that I'm in more places, therefore kind of gets smaller. The probability that I'm in more places. So the probability, say for example, if I walk away from here, say for example, the probability that I go to school, that I go to the local school, has got a certain probability associated with it, or go to the library or whatever. So basically, as I move away from where I started, I can go to more places. So the probability of me being in each place will get smaller as time goes on. But as I go backwards in time, there's less places where I can be because it actually physically takes me time to travel to a particular position. So as I travel backwards in time, okay, I'm certain of where I start. So in other words, my probability of where I am gets bigger. Yeah, because there's less places that I can be, so therefore each place that I can be kind of gets more likely. Okay, it's more likely that I'm in a certain place where I go backwards in time because I've only just set off, if you like. So basically, right at the very start, I know exactly where I am. So this is what this Dirac delta function is basically saying. If you followed that, well done. So effectively, what I want to do is I want to show that my probability as t goes backwards in time, so as t goes backwards in time, I want to show that my probability approaches this Dirac delta function. Now, in order to do this, I need to show two things. First of all, I need to show that, I've got probability of xt, so I need to show as t approaches 0 from the positive direction. So I need to replace t with 0 from the positive direction. And as I go backwards in time, my probability equals 0 when I'm not at my start position, which I'm just going to take to be 0. So let's say I start at 0. This is x. Okay, so at t equals 0, I mean 0 plus is kind of the mathematical definition. If it's more appropriate for you, if you just want me to get rid of that plus there, then that's absolutely fine. Just want to ignore that plus, that's absolutely fine. Okay, so in other words, at point t equals 0, I'm at my start position. So the probability of me being anywhere other than my start position, so at t equals 0, I should be at my start position. I know I'm at my start position, which I've just taken to be 0. So the probability of me being over here is 0, or the probability of me being over here is 0. This is the first thing which I need to show. I need to show that if time equals 0, I'm at my start position. So in other words, my probability of me being in a position anywhere other than my start position, so probability I'm anywhere other than my start position is x equals 0, probability that I'm at anywhere other than my start position is 0. Okay, so that's the first thing which I need to show. Now this is actually really easy to show because remember what my probability of x given t was. It was my probability density function, which I defined a few videos ago now. It was 1 over 4 pi dt, square root of 1 over 4 pi dt, e to the minus x squared over, is it 4 dt? Let me just double check. Yeah, it is. So basically as t approaches 0, so in other words, if I just plug a value which is really close to 0 in, or better still, I could plug 0 in. That would give me a good feel of what happens as I approach 0. If I plug 0 into this thing, therefore this becomes 0, so this is times 0, and this becomes 0 as well. So this is times 0. So basically what do I end up with? I end up with the square root of 1 divided by 0, effectively, because this denominator now becomes 0. So the square root of 1 divided by 0 is infinity. Okay, don't really worry too much about that. I'm more interested in what my exponential term is doing. So again, this denominator is 0, so therefore it's x squared divided by 0, so therefore this becomes infinity, so minus infinity this becomes, so it's e to the minus infinity. So what is e to the minus infinity? It's 0. Because basically if I put in a really big value for this, okay, I mean basically what I'm saying is that as I become it's negative infinity, so therefore it goes to 0. Basically, if you take the limit, you can see that. I'm not going to really justify that, but that is the thing, okay? E to the minus infinity is that, okay? Okay, so as t approaches 0, so I've basically shown that the probability, which is that thing, approaches 0 as t approaches 0, the probability approaches 0. So good, I've shown that. What's the second thing I have to show? The second thing I have to show is that basically the probability approaches certainty as I move to, the integral, it's like the Dirac delta function. So as I'm at my point x equals 0, okay, the area underneath my Dirac delta is 1. Okay, so the area underneath it should be 1. So in other words, how am I going to define that? So the area underneath it should equal 1. So the area underneath that's infinitely large spike should be 1. That's my Dirac delta function. It's a little bit more awkward to show. So this is what I need to show. I need to show that the probability of xt, okay, over my whole range, because of course it'll be 0 over here and 0 over here, okay, with respect to x, I need to basically show that that is 1. I need to show that that is 1. So basically when I'm at my start point, over here, therefore that should be certainty. I should know exactly where I am. I should be at my start point. Okay, a little bit more difficult to show. I have to basically use standard normal distributions, but let's work through it. We'll recall that for a standard normal distribution, so the integration of e to the minus x squared over 2, my variance effectively, sigma squared, with respect to x, okay, is equal to square root of 2 pi sigma squared. I'm not going to justify where that comes from. You can kind of ask a statistician where that comes from, but it's basically just a normal distribution. It's just a normal distribution, because that looks like a PDF of a normal distribution, somewhat like that anyway. And if I take the integral of that, then that's basically what it comes out as. I'm not going to ask you why. I mean, it should be 1 over square root of 2 pi sigma squared over here, and that should equal the area underneath the probability function, so the area underneath the whole curve. This is a normal curve. The area underneath the curve should equal 1, okay? So therefore, if I just multiply through by this constant effectively, then therefore it should just equal square root of 2 pi, is it 2 pi? Yeah, 2 pi sigma squared. Yep. So basically, this is the standard result that I'm going to use, because what's my p? Well, p is equal to, if I just rewrite this integral out again, so the integral of minus infinity to infinity, I'll just drop that because that doesn't actually matter that much. It's just over the whole range, okay? This is 1 over square root of 4 pi dt e to the minus x squared over 4 dt. Okay, and I want to differentiate that with respect to x. Okay, and I want to show that's equal to 1. Okay, well, if I take this out the front, so take that thing out the front there, it's just a constant, it's not involving x, so I can just treat it as a constant and get it out the front. Okay, so therefore I'm just left with that thing, right? Well, that looks remarkably like that. So that in there looks remarkably like that. So I want to basically show it's equal to 1. That in there looks remarkably like that. So basically, if I let, so I've got, what have I got? I've got my minus x squared and minus x squared there. So that's fine. I can leave that alone. But if I let 2 sigma squared equal 4 dt, so in other words, that denominator equals that denominator, yeah, then therefore I can just make a direct sort of thing, that just for the moment that constant comes along for the ride. So I end up with, I'll just write that constant out again. Okay, so then I don't have to worry about it again. So 4 pi dt. Don't worry about that for the moment. Okay, but times by should be then times by this, where I've just let 2 sigma squared equal 4 dt. So therefore, if I just rearrange this, I'll just write it as pi 2 sigma squared. This is equal to the square root of pi times 2 sigma squared, which in this case is 4 dt. So 4 dt. Okay, it's 4 dt. So therefore, just by using that standard result, that thing is the same as that thing. Yeah, if I just rewrite that now around the other way, so 4 pi dt. So therefore, that thing's the same as that thing. They cancel. So therefore, this just reduces down to 1. So just by using the standard result of a normal distribution, then I can show that my probability, the integral of my probability over my whole range, is just equal to 1. Which I've done. So great, okay. So there we go. I've shown the two things that I want to show. I want to show, first of all, I've shown that it satisfies the initial conditions, because I've shown that my probability approaches my Dirac delta function. I've shown that, my properties of my Dirac delta function is that basically at the point x equals 0, or close to the point x equals 0, I basically end up with this infinitely large spike at the start position. So at my start position, I end up with this infinitely large spike. Okay, so basically, if I'm at anywhere other than at the origin, effectively, because that's where I start, that's where I presume to start. So for anywhere other than where I started at, my probability of being there should be 0, and I've shown that just by taking the exponential of minus infinity. It's shown that by taking the exponential of minus infinity. Then I've shown that actually the probability as I approach 0, that basically the probability of when I'm at 0, I should replace that with 0. Okay, should have replaced that with 0. So probability is when I approach 0. then therefore the probability of me being at the start position x equals 0, that should equal 1. That should equal 1. And I managed to do that by basically using the standard result from a normal distribution. Okay, so therefore I've shown what I've wanted to show. I've shown that, you know, P of xt satisfies the initial conditions. So I've satisfied that, and I've satisfied the satisfies my diffusion equation. So I've found the solution. I've shown that it satisfies the initial conditions. So therefore I can say that that is indeed a solution to my diffusion equation. Now in the next video I'm going to look at the, because if you remember the diffusion equation, just get a spare page. So the diffusion equation was this thing: the derivative of P with respect to with respect to T, okay, is equal to D, lots of the differentiation derivative of P with respect to x squared. Okay, so that was, if you like, part of it. The thing which I actually wanted to solve was my drift diffusion equation, which kind of modelled the whole thing. So basically this was the case when I was taking equal size steps to the left and to the right. So in other words, when L equals R, so my left steps equals to my right steps. But this thing was, if you like, my whole, when I was kind of biased to move towards one direction over another. So I was taking more larger steps in one direction than another. And it was the derivative of, just trying to remember, was it P with respect to X? Yep, dP by dx plus my diffusion term, so d2p by dx squared. So now what I want to try and do is I want to try and solve that thing, and that's going to be done in the next video.